Okay, here's what we're going to do today. I'm going to give you several examples of a string fixed at both ends. I'll give you several examples of problems for you to practice them. Then we're going to learn about standing waves and tubes. We're going to talk not about guitars and violins. We're going to talk about clarinets and flutes and trumpets and things like that. That is standing waves and tubes. But first, let's go ahead and do some problems involving what do you call strings fixed at both ends. Here, I'm going to remind you, this is in your notes already, but I want to redraw this because I like to refer to this, number one. And number two, I want to show you how quickly you will get at drawing this stuff, because there's going to be a lot of problems that only a drawing will get you through. I want to remind you the first harmonic looks like this, like jump rope. This is the first harmonic. And if this distance from there to there is equal to L, it turns out that the fundamental frequency is the speed of the wave over 2L. And the reason for that is because the fundamental wavelength is equal to 2L. That is, if the length of the string happened to be 1 meter, then the fundamental wavelength is 2 meters. And then we get our second harmonic, which looks like that. And the second harmonic frequency is just 2 times the first harmonic frequency. And then we end up with the third harmonic. Alrighty. And the third harmonic is equal to 3 times the first harmonic. And we even have a fourth harmonic. You'll notice the fourth harmonic has 4 antinodes. The third harmonic has 3 antinodes. And we end up with the fourth harmonic being 4 times the fundamental frequency. This is the second harmonic, third harmonic, fourth harmonic. Now, we're going to talk, wait, I need to give you some problems to do. Here, just a second, where did I put my, here it is. Okay. Here comes example number 2. We already did example 1 yesterday. I've got a string fixed at both ends. The tension is 600 newtons. The linear density is 1 kilogram per meter. The length of the string is 0.8 meters. And I want you to find the fundamental frequency. Please do that now. I'll give you a hint. You will have to use this formula. Speed of a wave on a string equals tension over linear density. Good luck. I'll give you 60 seconds. Okay, time's up. I hope everyone plugged in 600 newtons here and 1 kilogram per meter there, so you get approximately 24.5 meters per second. You guys okay with that? And then hopefully if you did V equals F lambda, you got 24.5 meters per second equals that fundamental frequency times the fundamental wavelength. And I know that whatever the length of the string is, the fundamental wavelength is twice that length. So I know this is going to be 1.6 meters. And so I get 24.5 meters per second over 1.6 meters, which, by the way, if you're the type of person who plugs into this, that's okay as well. You'll get 24.5 over 1.6 meters. And so this equals F1, which is equal to approximately 15.3 hertz. Did anyone hear? Did I go too fast? Anyone get 15.3? Hey, yay, good for you guys. Hey, any question or problem on this? All right, then, hey, here comes the next question. Example number 3. Multiply tension by 9. So I'm going to take this tension and multiply it by 9. You've got to choose between increase or decrease frequency by what number? Please choose. Do you increase or decrease the fundamental frequency, and by what number? Good luck. All right, time's up. Tell me, do we increase or decrease the fundamental frequency?
Increase.
Good, increase. You have a sense already that if you increase tension, you increase frequency. So you know it's going to increase. Now, by what factor?
3.
3? What? How'd you get 3?
Square root of tension.
Good. You guys okay with that? Square root of 9. If I put a 9 here, the square root of 9 is 3. I'm going to have 3 times what I had before. And if I triple my velocity, since the wavelength is staying the same, because the wavelength is just determined by the length of the string. The wavelength stays the same. If I triple my velocity, I triple my frequency. So that's going to be my 3. Okay, you guys good on that? Okay, then here, let's do another example. Here comes example number 4. String has length 1.2 meters. Find distance between. Find the distance between an adjacent node and antinode of the 5th harmonic. Find distance between adjacent node and antinode of the 5th harmonic. So I hope you see, imagine like looking at this, like looking at the 3rd harmonic, I'm asking for the distance between there and there, the distance between an adjacent node and antinode, but I want this for the 5th harmonic, and I urge you, draw the 5th harmonic. Don't use your cleverness, just draw the thing.
It's so cold in here.
Really? How many people say it's cold in here? How many people think the temperature is just right? Right on. Did you notice the relationship? Guys, just right. Girls?
I mean, my toes are a little chilly. Not me.
I think it's because you're wearing long sleeves and pants.
Yeah, so monster like me. But I don't know
Do you know how to approximate a series without the Ranger? Do you know how to approximate a series?
Kind of.
Isn't it like S minus S of N is greater than the error?
Everyone's here today. Oh, how fun.
Are you sure?
No. Has a Mr. Shane question.
That's a my notes question. I didn't take. Oh, here it is. S minus S.
Okay. Now, are you okay? It's okay to draw the 5th harmonic first and then pretend that that's the length of your string? You don't have to choose the length of the string and then try to draw the fifth harmonic after that, because you got to be pretty darn good to do that. But anyway, are you okay that that's the fifth harmonic? 5 antinodes. Okay? Fourth harmonic has 4 antinodes. And then I'm gonna, well, someone tell me, what'd you get as the answer? What'd you get? What'd you get, Noelle?
0.12 meters.
She says 0.12 meters. That's probably wrong, but how many people agree with her? No one agrees with her. Come on. It's right. How many, now that you know that it's correct, how many people agree with her? What?
No.
How many people were able to draw the fifth harmonic? Okay, yay. And then, did you divide this up? Here, I'll use a different color. Let's use red. Did you divide this up? Node, antinode, node, antinode, node, antinode, node, antinode. I should have asked Noelle about this, but. So Noelle, is that what you did? So, okay. Did anyone do it this way? Anyone just divide it? Thank you, Cole. You and I think alike. That's beautiful. And then once you divide it like this, what do you do? What's that? Yeah, divide by the number of these thingies. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Divide by 10. I'm dividing a 1.2 meter string into 10 parts. This is the sort of problem my 3rd grade daughter is dealing with right now. She has a little bit of difficulty with it, you know? But yeah, 1.2 meters divided by 10, 0.12 meters. You guys okay with that? Okay, here, let me give you one last problem. Here comes example number 5. We'll go through this one. Just give it your best shot. You know, we're playing Pictionary. Tell me what I'm drawing.
What it is.
Guitar.
Yeah, you're right. It's a
A what?
guitar.
You look like a plastic.
At first I thought it was
Okay. So I have a particular string, okay? And this string, from the distance from the nut to the bridge, is 0.8 meters. You guys okay with that? 0.8 meters, okay? And it turns out that this string has a fundamental frequency of 220 hertz. Alrighty? My question to you is this. I want to fret that string so that I get a frequency of 262. So somewhere, I'm going to fret this string so that the length of the string is now shortened. And I want this frequency to be 262 hertz. Okay? What distance do I need to have between the fret and the bridge to get a 262 hertz tone? Good luck.
The answer is 4.
4?
4.
What are you thinking?
The answer is
Crazy.
4.
You crazy.
Is the answer not 4?
No.
I think you're wrong.
Yes, honey? Yes.
If it was 4,
You know what?
how
Yes.
is it shorter?
You gotta.
0.8.
4. Maybe 0.4.
Oh my god,
The
Dad.
Did
answer
Amani
is 4.
punch you in the eye or something?
I'm going to
The answer is 0.4.
Oh, darn Amani.
Mr. Shayna Gavin has the answer.
No, I don't.
Really?
No,
What's the
no,
answer?
no, no, no.
He said it's 4.
No.
Cool.
Yeah, you
4.
can use my.
Yeah, 4.
Crazy.
I'm not crazy. You're
Hey
the one
guys,
crazy
if
one.
anyone's stuck on this, tell me, what am I gonna, I know the length of the string, I know the frequency, what am I gonna find first?
Lots.
Yes, speed. You're gonna have to find the velocity. And by the way, if the length of the string is 0.8 meters, what does that make the fundamental wavelength? It's not 0.8.
Oh, okay.
Say that again, Noelle? Thank you very much, Noelle. You guys okay with that? 1.6. So you can do v equals f lambda, find the speed of the wave, but you're gonna have to do, 1.6.
You know what? I'm not even trying right now. I was doing calculus.
Yeah.
Thanks, buddy.
No clue. I don't even have my notebook.
Wait, in calc or in
Oh, in calc, yes I do.
Might be the same as 1G. Probably the same as 1G.
Can I have my notebook? Red notebook.
No, I didn't get that. Yeah, I didn't get that. I blame myself.
Okay. The speed of the wave on the string is 352. So now I'm going to do V equals F lambda again. And I got 352. I want a frequency of 262, and I need my wavelength. So I got 352 divided by 262, and I got 1.34 meters. Yay, 1.34 meters. That's what this is, correct? 1.34 meters? Oh, right, you guys. Because I just found the wavelength. And remember, whatever the wavelength is, the length of the string is half of that wavelength. So yeah, it's 1.34 over 2. That is 0.67 meters. Yeah, that's the answer, 0.67. Any question or problem on that?
Like the camera knowing?
Okay, then it is time for us to learn about standing waves and tubes. Here we go, standing waves and tubes.
Tubes. Can I erase this? If I still need it? 1 second, Cheyenne is still thinking.
One, erase it.
Yeah, there it was, there it went.
Oh my gosh.
You good? Yeah. All right.
These are my notes.
Okay, great. We're going to learn about two types of tubes. Tubes open at both ends. Tubes open at both ends, and tubes closed at one end. First of all, tubes open at both ends. Some examples of tubes open at both ends are flutes, piccolos, organ pipes. Those are all tubes open at both ends. This is a tube open at both ends. I am now going to play the tube. You guys okay with that? You can hear that tone. It's a tone. Okay. Imagine a flute. Someone describe for me, how do I play a flute?
Sideways.
Sideways. Good. What else? How do I blow? What's that, Giancarlo? No, tell me, how do I, here's the mouthpiece of my flute. What do I do?
Blow air across or into.
Thank you. Blow air across. Really, you're blowing air across the hole, right? So you see, and so this is a flute. It's the same thing. I'm blowing air across the hole, right? We do that so that we get a tube open at both ends. One end of the flute is open to the air because you're blowing air across it. You're not covering it with your mouth. And the other end is open as well. So a flute is a tube open at both ends. If you stick your mouth on the hole, you're not going to get any sound. You got to blow across. You guys okay with that? Okay, let's go ahead and look at the math of a tube open at both ends. Here's my tube. My tube open at both ends. A tube of length L. Oh, I'm not going to write that there. Okay. That's fine. Tube of length L. Let me ask you this question. It's not a very good looking tube. Oh well. What is the air pressure right here where my finger is pointing. What's the air pressure right there? What's that?
Never mind.
What is the air pressure?
One?
Yeah, 1 ATM, 1 atmosphere. And are you guys okay? Since the air pressure in the room is 1 atmosphere, the air pressure right there is 1 atmosphere. Okay, great. I am a human being. I'm a puny human being with a little puny lungs. I'm going to blow. Am I changing the air pressure very much right here?
Not a lot.
Really not at all. I'm not big and strong enough to change the air pressure of the entire room by blowing, right? The air pressure of the entire room is 1 atmosphere. The air pressure right there is 1 atmosphere. It's open to the room. It's 1 atmosphere. You guys okay with that? Now, when I blow, I'm altering the air pressure a teeny bit in the same way that, remember, who's my spring buddy yesterday? I forget. John Carlo? Okay, remember how me and John Carlo were making the standing waves, and although I was a node, I still was moving a little bit because I needed to enter some energy into the system, so I'm moving a little, but for the most part I'm a node. And that's kind of what's happening here. Yeah, I'm changing the pressure a teeny bit by blowing, but not much. But it's enough to, excite the system and get energy into the system. So I want you to see that when dealing with pressure, when I'm looking at the pressure inside the tube, when I'm looking at the pressure inside the tube, I'm going to have a node at the ends open to the air. Okay? Node there, because they're open to the air. It's 1 atmosphere. 1 atmosphere in the room, 1 atmosphere at the openings. Okay? But what about in the middle of the tube, where it's kind of shielded from the air pressure of the air? It's deep inside this tube. I can make this air pressure high and low. And so when I set up a standing wave, I'm going to get rid of this. When I set up a standing wave, I end up getting an antinode in the middle. Remember, I'm dealing with pressure. So what does a pressure antinode look like? Well, it's going to be a region that alternates high pressure, low pressure, high pressure, low pressure. That is, it'll be low pressure, rarefied, and then what? Oh, okay. And then high pressure, and then low pressure, and then high pressure. And I'm just alternate back and forth between low pressure and high pressure, because these are compression waves. These aren't transverse waves, these are compression waves. High pressure, low pressure, high pressure, low pressure. Well, the problem is, it's really hard for me to draw that, So I would like to symbolize an antinode here in the middle, a region of high pressure, low pressure, high pressure, low pressure, without having to draw a million little dots that change. And the way I'm going to do that is borrow from how I symbolize antinodes with a string fixed at both ends. I'm going to say, you know what? I'm done with the dots. I'm just going to draw this. And that way it tells the world that I have an antinode here, which means I'm going from high pressure to low pressure to high pressure to low pressure without having to draw a bunch of dots. You guys okay with that? Okay, well, let's go ahead and get the next harmonic. Remember, I'm going to have a node here and a node there. I have a node at the ends, 1 atmosphere pressure of the room. But now I'm going to have 2 antinodes in between. I'm going to have high pressure node, high pressure node. Antinode, antinode. This is my first harmonic. This is my second harmonic. As long as I keep nodes at the ends, I'm okay. I can have antinodes, as many antinodes as I want inside, because the inside is protected from the outside air. In fact, let's go ahead and draw the third harmonic. Node, node, antinode, 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 node. This is the third harmonic. Mathematically, do you notice something about a string fixed at both ends and a tube open at both ends?
what word would you use to describe them mathematically? What do you think? Here's first harmonic string at fixed at both ends. Here's first harmonic at a tube open at both ends. Second harmonic for string, second harmonic for tube. What word would you use to describe them, their relationship?
Just one?
What's that?
I said just one.
Okay, just
No, I'm
one.
just saying like just one word.
Yeah, one word would be good enough. Yeah, Giancarlo? What's that? What do you say? Yeah, thank you. Is anyone thinking the same?
That's two.
Oh, that's 2 words. Anyone thinking of the?
Equal.
But I'm showing you this to convince you, hey, tube open at both ends, mathematically, is identical to a string fixed at both ends. If you're going to have a node on both ends, I don't care if you're a tube or a string, all of your harmonics are going to look the same, right? So I just want you to see that this is mathematically identical. Mathematically identical to a string fixed at both ends. It's the same darn thing. So I'm going to derive what the frequencies of the first, second, third, and fourth harmonics are for a tube open at both ends. Are you ready? Boop, there it is. Just use that, right? I'm going to give you a bunch of problems to do now concerning a tube open at both ends. It was examples 2, 3, 4, and 5 that I did earlier. All the numbers will be identical. So are you guys done, right? Are you done yet? Good, you're done, because you already did them, right? Okay, I hope you're getting what I'm talking about. That I don't have to do this again, we did it already. Because it's identical to a string fixed at both ends. But now, a tube closed at one end, that's a completely different situation. Clarinet, trumpet. Those are tubes closed at one end, okay? Because whereas a flute, I'm having to blow across the mouthpiece to make sure I keep that open, right? What do I do to the clarinet? I just stick one end in my mouth, right? I totally close off one end of a clarinet. Trumpet, just stick my mouth on the end. That's not open, that's closed. You see what I mean? Do you see how a clarinet and a trumpet is different from a flute? You're closing one end because you're sticking it in your mouth. Alrighty? So what that means is I'm going to have a tube that looks like this. One end is open to the air. So that's going to be a node. The length of this guy I'm going to call L. But the other end is completely protected from its surroundings. The other end, I can make it any pressure I want. And again, I'm doing pressure. Tomorrow I talk about displacement, but I really want you to think in terms of pressure. I think it's easier to picture. And so what happens is I end up developing an antinode right there. At this very end of the tube, because it's protected from its surroundings, I can have an antinode there. So the first mode of vibration, the first harmonic, looks like that. Node here, antinode there. There's my first harmonic. First harmonic. So tell me, what fraction of a wavelength do I have there? Yeah, 1/4, not 1/2. 1/2 I would have to be to there. From the there to there, that's only 1/4 of a wavelength. Equals L, which means that wavelength equals 4L. So when I get my fundamental frequency, that's going to be V over lambda. That's going to be V over 4L. That's my fundamental frequency of a tube closed at one end. So tell me, what's the relationship between a fundamental frequency of a tube closed at one end and an identical tube that's open at both ends? What's the relationship of the fundamental frequencies? You guys see that this guy's half. If you're thinking of music, this guy's one octave below that guy. Consider a clarinet and a flute. They're about the same length. Which one is lower pitched?
Clarinet.
Yeah, the clarinet, right? In fact, approximately an octave lower, because it's half the frequency. Consider this tube, right? I'm now going to cover one end. Can you hear the difference? Right. So if someone asks you, flute and clarinet, they're about the same length. Why is a clarinet so much, lower pitched than a flute? What are you going to tell them?
Because one is covered.
Thank you. Because the clarinet is closed on one end, because you stuck one end in your mouth, right? And thus it's going to have half the frequency of a flute. Does that make sense to you guys?
Yes.
Yes, that's all it is. The difference between and. Okay. Well, let's go ahead and get the next harmonic. I want to remind you, since this side is open to the air, it's going to be a pressure node. Since this side is protected from the air, it's going to be a pressure antinode. But now I'm going to get the next harmonic, which means I'm going to have another antinode and another node in between. That is, it's going to look like this. There's my next harmonic. I have node, antinode, but I have another antinode and another node in between. So what fraction of a wavelength is this?
3/4.
Thank you very much, Gavin. 3/4 lambda equals L, or lambda equals 4/3 L. So I get this frequency equaling V over lambda, which is the same as V over 4/3 L, which is the same as 3 times V over 4L. Okay? Keeping in mind that you can find the harmonic by just multiplying which harmonic it is, by the fundamental frequency. Which harmonic did I just find here? Thank you, Fatima. Say it again. You guys okay? I just found the third harmonic. This is the third harmonic. Where's the second harmonic? I'll tell you, there is none. One of the things that makes clarinets and saxophones and trumpets sound as bright as they are is the sound is not muddled by having even harmonics. All you have with these instruments are the odd harmonics. Only have odd harmonics. Here, let's go ahead and get the next harmonic. Still got a node here. Still got an antinode there. And so now I'm going to have Alrighty. What fraction of a wavelength do I have now? How much of a wavelength? From there to there?
1 1/4.
Thank you, 1 1/4. Thanks, Imani. 1 1/4, or 5/4. 5/4 wavelengths equals L, which means my wavelength is a 4/5 L. So this frequency is gonna be V over 4/5 L, which is the same as 5 over V over 4L. 5 times V over 4L. So which harmonic is this guy? Fifth harmonic, yeah. Any questions or issues on a tube closed at one end? Then are you ready to do some problems? Good. I heard one sure, and that's good enough for me. Here we go. Here, I'm gonna erase this since that drawing there is good enough for a tube closed at both ends. I mean, a tube open at both ends. Of course, what are you gonna get from a tube closed at both ends? Nothing, right? Because no air comes out, no air comes in. You can't excite vibrations with a tube closed at both ends unless you bang on the side of it. Okay, great. Here we go. Example number 1. I've got harmonics. I have harmonics at 450 hertz, 750 hertz, and 1050 hertz. I have harmonics at those frequencies, but none in between. That is, I don't have any harmonics between 450 and 750. Oh, I should have written this up here. Hey guys, I don't know if you're going to put this on your paper, but I really want to make it clear that this is the 3rd and the 5th harmonic. Okay, here's my question. Part A, please get me the fundamental frequency. And then part B, is this a flute or a clarinet? Which is it? Good luck.
You're so white. You too. Good job, Lucy. So many freckles. I wish I had freckles. I want freckles.
How does it work for you?
Tiffany has freckles.
For you, not no idea. You have too much Filipino. Too much Vietnamese in you.
Take that back.
Yeah, too much Filipino in you.
Gavin, the grades learning physics. The grade is physics.
Okay, time's up. Who got an answer? Anyone want to posit an answer? What do you think it is? Just use your intuition. Yes, DeAndre. DeAndre says 150. How many people agree with him? Okay, that's good enough. 4 people. DeAndre, how did you know?
Well, I mean, they're, well, 150 times 3 is 450. 150 times 5 is 750. 150 times 7 is 1050.
Beautiful. Someone else who got 150, how did you know? Yeah, Cole.
I did 450 divided by 3, got 150.
Beautiful. And then did you notice that all these other guys were multiples of 150? Great. Did anyone, speaking as a math teacher, did anyone just get the greatest common factor of those 3 numbers?
Oh.
What's the biggest number that divides evenly into all of them? Did anyone do that? Was there an alternate way? Did anyone see that the difference between 2 successive numbers was 300?
Yeah.
Okay, good. And so you kind of dealt with that. Yeah, beautiful. So if the difference between these is 300, what's the harmonic below this going to have to be? Yeah, 150. That's beautiful. However you thought of it is fine. Some of you may have just used your intuition. You may have just thought 150 without even knowing why. But you're correct. So now tell me, is this a flute or a clarinet? How do you know? How do you know it's a clarinet, DeAndre?
I just know, I mean.
Good enough.
There's none in between, yeah. No
Okay,
harmonics in between.
say again?
There's no harmonics in between.
Thank you, there's no harmonics in between. To say it more like the way I taught it, go ahead.
They're odd. They're all odd.
Yeah, we only got odd harmonics, right? We've got the third harmonic, the fifth harmonic, and the seventh harmonic, and nothing in between. So it must be a clarinet, which only has odd harmonics. Okay, hey, here's the last one I'm gonna give you, okay? Here's example number 2, okay? A tube open at one end, so I guess I'll say a tube closed at one end. A tube closed at one end is 1.2 meters long. Get the distance between adjacent node and antinode of the third harmonic. I'll give you 60 seconds. What's the distance between adjacent node and antinode of third harmonic? Okay, time's up. What'd you guys get? What's that?
0.3 meters.
0.3 meters? How many people agree it's 0.3 meters? A couple. Did anyone get an alternate answer? What'd you get, Anais? 0.4 meters. How'd you get 0.4? Thank you. Do you see how essential it is to draw a picture? Now, you didn't have to because there was one up there, but oh, you did. Good for you.
Well,
But
no, it was next.
okay, good. But I do want to tell you, when you're doing an exam, you must draw a picture. Your chances of getting the answer right are very, very high, right? And so here's node, antinode, node, antinode. And so you see it divides the tube into 3 equal parts. Now, if you're Cole, it was 4. He just counted 4 for some crazy reason. But it's actually 3. And so you get 1.2 over 3, which is 0.4 meters. You guys okay? And Cole, is that what happened? Or did you just do 1.2 divided by 3 and you got 0.3?
No, I ended up counting 4.
You're crazy. I have to tell you, I did that last period. I literally did this and counted 4. I don't know why, but I counted, I guess because there's 4 lines, but I literally counted 4 and I got the problem wrong. It was so embarrassing, but no one in video land will ever know. So are we good? Okay, good luck you guys. Bye-bye.